Good day, everyone, and welcome to my YouTube channel. This is Lungile of Bonds Engineering. Bonds Engineering is a small company aimed at basically opening up the chemical engineering discipline to especially pre-disadvantaged communities, starting with the learner, creating content and basically making information accessible, especially to young students before they go into official training, like in your TVEC colleges, in your universities, and so forth. And the way that I've been hoping to do this is through YouTube videos like this, where once people are in the formal training environment, they're able to find a soft place to land on where they can find information regarding their coursework and so forth. So my focus so far has been chemical engineering design. Hopefully, as we grow, as we get more people involved in the project, we will start looking at other disciplines as well. So I've been away for some time. I think the last video I made was probably a year ago or so. But the one compliment that I always get is my videos have helped so many people get started with their design projects. And I always get requests to create more. So this year I've been dealing with a few students who were designing the production of ethyl benzene. And I found that to be an interesting problem in that it is simple in its nature, but has the opportunity to be opened up in such a way that a lot of concepts can be explored just from that one project. So I've decided to make it my project of the year, where I will start from the beginning in terms of design basis up to as detailed as possible engineering design. And I know with students it only ends at conceptual design, but I would like to take this opportunity to make multiple episodes to basically take through the young child on what actually happens or an approximation of what happens in the design office, how an idea of a process is taken from concept to final implementation. And in between, I'm hoping that students, when they see these videos, they will be less intimidated in terms of what they need to do for their design projects. So let's not spend too much time talking. I want to get started. So as I said, the main purpose of this is to, by way of example, trying to find a midpoint between what would be happening in an actual engineering office and what is required on a university level, on a design project level. So I'm going to try to be somewhere in between. However, you will see that in most cases, especially when it comes to reactor design and so forth, I will be simplistic in terms of your design equations and things like that, to leave some of that work to the student to go back to the design textbooks, to go back to their reactor theory, to go back to their thermodynamics, to go back to their particle theory, separation theory, all of that. But the main aim is to open up your mind so that you are able to get started, because that's where I see most students struggling. So let's get started without further ado. So the first thing I want us to look at is the design basis, right? And in order to do that, I want to look at a definition, a nice definition I found online for what a design basis is. But before we get started, I'd like us to just admire and understand the beauty of the field we're in, chemical engineering, you know? And I found a very nice statement in the design textbook by Sinot and Towler that basically says that starting from vaguely defined problem statements, right, e.g., the client's needs, experimental results, chemical engineers are able to develop an understanding of the key physics relevant to the problem, right? They can then use this to develop an action plan, right, which has a potential to lead to a financial income. That for me is very beautiful. And the other one that I like using, and this one I can't even quote because I don't remember where I heard it, like, repeatable occurrences such as a reaction of hydrogen and nitrogen to produce NH3 have created such a huge one of the largest industrial processes ever, which is the harbor process. And what I like about this is once you find a repeatable process, right, you move from what is repeatable to predictable. And once you are predictable, you can move to scalability. And that's where the big money comes in. But obviously, it's not only about the big money, it's about solving problems. And, as South Africans, as previously disadvantaged, it's important when you are going through your career to be also thinking that how can I be a source of solutions for the community I'm coming from? And part of that is creating large scale processes, because large scale processes create large scale employment, but also they create large scale solutions for problems, right? So let's delve into the design basis, right? So a design basis is a document that fixes the constraints of the project, right? It looks at your capacity, your operating hours, and the targeted quality, right? It also defines the utilities that will be available to the engineer. And then it also looks at constraints that will arise due to the environment. And then it sets a set of design parameters, right? And what this does is it removes discretionary thinking and discretionary decision making from the engineer to base things on actual reality, things that are set by constraints that are described above, which then obviously now ensures that your design approximates reality rather than something that is thumb-sucked and comes from pure science fiction. Right. So I think now we can go into our design basis, because what I'd like us to cover today, I'm going to try to make this an hour session, depending if the recording session will allow. I'd like us to go as far as from design basis to looking at the material balance required to get to simulation level, where we're going to end up producing a process flow diagram just on the simulation itself, not the official one, but also look at closing out the mass balance, and then finally just looking at energy balance considerations. Right. So let's get started. So the template that I have here, I developed myself. And the reason why I did this is to illustrate the fact that, yes, most of what we have is based on principles that were developed by the old engineers in 1960, found from data sheets that were probably long. But the point is, when you're starting up with your design is there, you just need to know where to find it. So this is a design basis where it shows you the key information that should be on a design basis. For example, general information, your measurement system, equipment numbering systems, your products that you created my own template. And the reason for this is just to illustrate to the young engineer that you're not fixed to what is already there. You're just supposed to use that as a guiding principle to ensure that everything that is required in an official design document is represented. But you are allowed to create your own template, make it look nice. So as you can see here, I've put in the general information. The project owner's name is GDC Incorporated. The contact person there is Mr. V. Chauke. The project itself is sitting in a plot in Siandani. Very important piece of information, because you need to know where the project is going to be, which will be relevant for information that will come down later. And then the measurement system, just that the system will use the metric system for all design calculations. And then now you then go to the scope of work, right? So in this case, it is required to submit to the client a detailed design of a plant that will produce 120,000 metric tons per annum of ethyl benzene, also known as phenyl ethane or ethyl benzol, right? Ethyl benzene has the chemical formula of C2H5, CH2CH5, I think it's CH5, not 3. We'll just confirm that. Is an alkyl aromatic compound, which is extensively used in the manufacture of styrene, right? Then we go on to look at things like design assumptions. So this is where now we spoke about a document that fixes the constraints of the project, where it looks at the capacity, the quality that's required. It looks at it looks at your utilities and so forth. So now we look at your design assumptions, right? Let's also add constraints to that, so that the quality required. So the molar the molar ratio of DIN to ethylene is 8:1. The plant will operate for 330 days per year. What I also included here is some of the assumptions that I will be making during the course of the design. Like, for example, for your simulation in Cocoa, I'll be using the Gibbs minimization energy via the Gibbs reactor model to approximate the reactor calculations, right? Other things you can add here is the product quality required. We can go 96% purity let's go by weight of ethyl benzene. Right? And then you can also, as we go, you can add other assumptions and other constraints that you come across when you're doing the design. Then the lecture numbering system will be used throughout the design. So you give a general format of how your line numbers are going to look. For example, here you would have the stream code. So for example, if you're flowing water, maybe you can say WAT. I think I have a table down here that has that information. So water we have as W. So in the case of water, you just have W would be a plant section code. So for example, if you probably want to, the code could be something like DME or DMIN, right? So that would be the triple X, or it could be a number. So you could give that section of the plant the code 0100, right? And then lastly, of that code, you can have triple X, which is your sequential numbering, which would be 0, 1, 2, 3, 4, 5. So, for example, it would be 001 and so forth. Then the same thing for vessel numbering, same kind of thinking, AA, triple X. So, for example, your AA would be your vessel code. So, for example, if you have a column, you would have C, and then sequential numbering would be 001, right? And then you would show your symbols, that's your nomenclature. So, EB would be ethyl benzene. So, what you then do is, going forward in your design, wherever you have any of these components or any of this equipment, this is what you're supposed to stick to. This is the code you will use in your process flow diagrams. This is a code you will use in your PNIDs going forward, right? And then you look at your products. Again, we met again the product purity. So we said 96%. We want the production rate of 120 tons per year. And then the raw materials, I purposefully left it empty, right? Because what we know about the raw materials is that you need to produce 93% ethylene. You have 100% pure benzene, and you are given 93% pure ethylene, but you're not given the quantities. You're not given you're given the acting temperature and pressure, but you're not given the quantities. So the whole point of doing the mass balance and doing the simulation is to get to a point where we can now come back and fill in this section. So as I said, in reality, this document is a live document, right? Meaning some of the information will be filled out as you go. It's not information that will be immediately available. As you do your design, you'll come back and put it in. So your design basis will be comprised of information that will come from the client, where the client says, this is what I want you to do for me. And then part of it will come from you, the constraints and as we said, the design constraints that you will set based on the information you get from the site, based on the information that you get from your design calculations, your limitations set by things like your what do they call them? Your design variables, your constraints such as degrees of freedom and so forth, right? This you can then come back and add to your design basis document. So for varsity level design basis document, 2 or 3 pages, that's okay. But now if you're looking at an actual plant, this document can go anything from 30 to 50 pages, depending on the size and complexity of the plant that you're producing, right? You're designing. Then we look at site information. So again, this has to be an approximation of what's happening in the place you're at. So we're talking about Guyana as a site. Guyana is a hot place, so your ambient temperature can range from low of 25 to a high of 41 degrees. Now you have to consider that. Why? Because it also fixes certain things like your cooling water, right? Because your cooling water, normal ambient cooling water is not put through any refrigeration. It's based on ambient temperature. So now if that day you're sitting with a temperature of 41 degrees, you know that your cooling water will be at a higher temperature, maybe you're 35 degrees, 36 degrees, somewhere there, which means in your design, you have to consider that. You have to consider the fact that your equipment should be able to handle that high temperature upset and should be able to handle a low temperature upset. Let's just say now you're designing a plant for a colder region, like your Cape Towns and all of that, where you get as low as 1 degree, 0 degrees quite occasionally. Your equipment, your heat exchangers, for example, should be designed in order to handle that low temperature if it's going to be using cooling water. Usually your cooling water is used in your cooling towers and so forth, right? Look at your humidity, which is important parameter for design as well, and you look at your maximum wind load, so for your equipment and so forth, right? Then the next thing, you look at your utilities and raw materials, so costs and things like that. And then this table is missing. There's something I updated just yesterday. I just want to make sure, but I forgot to save it. Just hold on a second. I had put in the utilities table as well and went as far as, let me try and open it from here. I'm hoping it is saved. I'm hoping it is saved as I want it. Yes, I had put in a nice utility table because the reason why I wanted it is just to go through it quickly as well. So, for example, you've got your low pressure steam at 618 kPa, you have the pressure, you know it's saturated, therefore you can get the temperature, right? And then you've got a high pressure steam, you've got the pressure, it's saturated, you can get the temperature. And with this, you know that steam can be used for heating and for cooling, depending on where you want to be. You've got natural gas. What would natural gas be used for? In the case that you need very high temperatures now, you can burn the gas in a furnace and use that heat for heating your streams that are required. You need to look at electricity. There are some cases where you cannot use steam or gas or whatever. You have to use electrical heating coils, for example. There's certain equipment like agitators, you're going to use electricity. So you need to look at the cost, right? You need to look at your cooling water. You need to look at refrigeration. Now, if you're designing a plant and it requires you to go as low as minus 100 degrees in temperature, you need to look at the utilities. Do you have that available? And if you don't, what do you do? So, for example, the lowest temperature we can design for in this particular design is minus 50 degrees. So that's a consideration. It's a constraint. That's why it needs to be in your design basis, because you know immediately once you come across a situation where, for example, a separation process requires you to be at minus 65 degrees, feasibility falls out the window. You can no longer do that, right? So that being said, this is how my design basis looks like. It's my template. It's how I'd like it to do. So you, as the prospective engineer, you're supposed now to do your own template. Look at what the information, but again, you need to make sure all the relevant information that is required in a design basis is represented in your document. Again, when I say make it your own, I don't mean now put in flowers and whatever. This is an official document, right? It needs to look official. So next, let's jump straight to the material simulation, but looking at the time, we might not be able to. So what I usually do before I start before I go into process simulation and any of that is I like to do the manual mass balances initially myself, right? So for example, we know that we want to produce 120 tons per year of ethyl benzene, right? So we'll convert that to moles per second, and that will come down to 0.03. So we all know unit conversion, right? And then what we'll then say is that if you've got the number of moles that are required of ethyl benzene based on the stoichiometry, you can then calculate the number of moles that will react of ethyl benzene, and no, the number of moles of ethylene, right? Then after that, you can look at your data that was given. You were told that your benzene to ethylene ratio is supposed to be 8, and the purpose of this is to minimize the production of side products like your diethyl benzene. So therefore, immediately you can calculate the total feed of benzene, which will give you 8 times the amount of ethylene, right? And by this, you know that the fact that you're going to have 8 times the amount of ethyl benzene in your system, right? It means your ethylene will most likely be totally consumed, right? In reality, this might not happen. You might find that you'll go as high as about 96% somewhere there. But from this, you immediately know that as a basis for your simulation, you know that you've got 100% consumption of ethylene, right? And then the next thing you can do is calculate your compositions. So not the compositions, but calculate the size of your ethylene stream. Because now you have the benzene stream based on the ratio that you have. Now you need to calculate the total size of your ethylene stream. So you've got the composition of the ethylene stream. It's got 93% ethane, and it's got 7% ethane. Ethane is in et, right? So what you'll then do is you will use that information. That total size of the stream will basically be the ethylene divided by the fraction of ethylene, right? And then that will be the total size of the stream, and then that will also allow you to calculate the total number of moles of ethane, right? The other thing we need for our process simulation will be your reaction temperature and your pressure, right? Your reactor pressure. So let's proceed. Once we have this, we can go on to your process simulation. But before we go there, what I'd like to show you as an objective once we're done is also to look at over design requirements. That in the case that after you do your simulation, you find that the downstream processes for separation will take away from the total product that will be going to your storage. Hence, if for example, your mass balance calculations say you're going to produce 120 tons per year, right? Some of that may be lost in the recycle, some of that may be lost in your flare. So we need to look at over design considerations as well. And then finally, other considerations such as product upgrade and maybe the need for such things as product fit heat exchange. So that's when now you look at heat integration and things like that. But let's jump into the simulation, and then hopefully we'll have enough time to produce the stream tables to close out the mass balance, look at energy balance considerations, when now you look at heat integration and so forth and so forth. All right, straight to our simulation. Going to start blank. It will be a bit slow. Hopefully, we'll move as fast as possible. But the first thing you need to look at when you want to do a simulation using, when you want to do process design or conceptual design using simulation, is you need to decide on a property package. Right? What is a property package? Basically, it's a thermodynamic set of equations that are used to predict. Right. So let me just go back, and I think that one I had somewhere. But basically it's a thermodynamic equation that is used to predict your stream properties and your equilibrium, your phase equilibrium, right? So why would you want to use a simulator, right? Why a simulator? So what simulators do, they contain subroutines for calculating component streams, physical properties, right? So they have subroutines based on those property packages talking about. Your simulator has a subroutine. It has a pathway that it follows, right? To calculate your physical properties of streams and also the phase equilibrium of the processes, right? So what it does, it takes manual calculations that would otherwise take days and days and days, especially for a large plant, depending on the complexity, into a few hours. The design engineer can be doing that in the comfort of his office, present to you the preliminary mass balance calculations that will allow for further complex designs, where now you can move from your conceptual design to your detailed design and to your bankable feasibility studies. So that whole conceptual design process has been compressed from days or sometimes even years down to a matter of hours, right? So that's the whole point of doing the simulation. So let's go back to property packages. Now, again, I did say I am going to move very quickly. Thus, I'm going to use a lot of shortcut methods. But what will be required of you as a design student is to actually go back to the source of this information. So if you go to your design textbook, there's a section, I think I have it open here, that actually deals with simulators. Yes, I do have it open here. So there's a same with most students that I work with. This information is available to them, but people don't take their time to actually read. This is an important section to read as it makes models and why we choose certain physical property models. But for the purposes of our presentation today, as I said that you're going to use, the first thing you do is you need to look at your components. Are they polar or non-polar? Right? If they're polar, then you're looking at are they electrolyte or non-electrolyte? If the electrolyte, then you're gonna select something like NRTL or pizza, but you'll see it in the simulation that you're using. If you're using non-polar, is it real or pseudo? Pseudo components are mainly things like where these are components that are derived basically, whereas your real stuff is your real stuff, like your alcohols and things like that. So with real components, you're looking at Peng Robinson, Radley Kwang, Suave, your Lee Kessler, Blocker, and things like that. So this is the shortcut method. Go look at it, go study it, and understand it. So let's set up the property package for a simulation. Hope this goes away. Thank you. So in order to do that, you'll go to your configure flowsheet. Then we'll add. Then we'll go TAA. That's my default. Don't ask me why. We'll go new. And then let's call this one production of ethyl benzene. Description, let's call it Siandani plant. And then model set. As I said, our options are Peng Robinson, Suave, Ridley Kwang, Wilson. My standard is always Peng Robinson, never giving me problems. So we're going to go Peng Robinson. Right? The next thing we're going to do is we're going to add our components. Right? So go back to our design. We know we have ethylene, benzene, ethane. Let's just make sure we have everything we need. We've got ethylene, we've got benzene, we've got diethylbenzene, and we've got ethane. Second, add. So we've got ethylene. There we go. We've got ethane. Where is ethane? C2H6. Ethane. We've got benzene. We've got ethylbenzene. Ethylbenzene. Let's go with the first one. Oh, no, this one without, but ethylbenzene. We've also got diethylbenzene. Diethylbenzene. Let me just type benzene. Ethylbenzene. We'll choose from one of those. Ethylbenzene. So make sure we choose the right one. Just gonna go with that one, diethylbenzene. We've got O and M, so we can choose, let's just choose one. Okay, then I'm gonna click OK. See if I have any warnings. Yes, want to assign the property package. Then we close it there. Right, so now we've got our property package. Now we start building our flow sheet, right? So to get your process stream, that is your insert stream function. So we've got two streams coming into our process. We've got the benzene stream and we've got the ethylbenzene stream. And then to stick to our nomenclature that we had decided on, we can go back to our design basis. And from our design basis, if we go back, we'll check your benzene is B and your ethyl benzene is EB. So let's just immediately stick to our designated. So we've got B for benzene and we've got EB. So what this does is it allows you to be systematic throughout your design so that each of the documents that you produce can easily be related to a previous document. And then what we have is the one thing that I forgot to include in the design basis is the fact that your pressure coming into the process was 20 bar and your temperature was 25 degrees. So we're going to use 298,15. So this is the benzene stream. So the benzene stream will have 0 ethylene. It will have 0 ethane. The mole fraction of benzene will be 1. Everything else will be 0. And in our mass balance, we used kilomoles. So we're gonna go kilomole. And if we go back to our spreadsheet, from the calculation, we'll see that your 1739, so we're gonna copy and paste that as it is. And then what you'll see immediately, right, is something that would be a painstaking amount of work where you need to go to your property tables, things like textbooks, like your Perry's chemical engineer's handbook, all this information where you'd need to figure out what phase fraction you're in based on the temperature, your overall properties such as your enthalpy of the stream, your liquid properties such as your density, your heat capacity. This is all the information that you need to now go and reference your property tables. Your simulator is now able to give you that specific heat capacity at that specific pressure and that specific temperature based on, as we discussed, the thermodynamic property packages that you're using. So that is the advantage that you have. The next thing is we're going to look at the EB stream. Again, it's coming in at 20 bar. I must remember to update my design basis to include the stream properties coming in. So we're looking at 298.15 Kelvin. Ethylene, we said it was 93%. And then the rest is 0. So once we fill in the rest, it will automatically calculate your ethane. And then we go back to our mass balance. And that should be able to give us our total ethylene stream. So it's not EB, this stream is supposed to be E because it's just ethylene, not ethyl benzene. Let's go back to our nomenclature. Ethylene is just E, so I just need to make that correction. We simply double click on that and we go E, right? So now, the next step is we need to get to reaction conditions, right? In our setup of our process data, we said that the reaction occurs at 450 Kelvin and the reaction temperature is 40 bar. So we need to get to those conditions. So we've got two options. We can do that individually, or we can combine the streams, right? And then after combining the streams, we can then heat it up or compress it and do all of that. Now, if you check, your ethylene is in vapor and your benzene is in liquid. So the first thing I would do is combine them and see what phase comes out after that. So again, my target is to do the reaction in liquid phase. So let's see what happens when I mix them. So usually what I like to do for presentations like this, I like to do each unit up as I go so that we look at the subsequent results of, and then immediately what you see is your phase that comes out of your mixer is totally liquid, And again, because now it's a mixture, right? We've now got ethylene, ethane, and benzene. In order for you to get your density, you would now need to use you need to use equations that would allow you to estimate your density. So either you would go group contribution method or similar to that. So hence your simulation will make your life easier in that sense. Then the next one we'll look at is your compression. Because no, we want to use a compression in this case, you would all right, got a bit of a disturbance due to network. So let me set up the screen again. We are sharing screen 2. Just want to ensure that we're recording, and yes, we are recording. So we got the mixer, and the next part would be to put in a pump to take us to 40 bar. Again, as I said, most of my stuff is going to be very shortcut. So you would need to look, is it possible to move from 20 bar to 40 bar based on your pump specifications? If not, you might need to do multi-stage pumping. We've added another unit. Just going to try and remove this. Then again, we're going to run 1 unit at a time. So run that. And now we're at 40 bar. We check our temperature. We've only gone up to 307 degrees from 298. Therefore, we will need a heat exchanger. I did mention in the design basis, or was it the design basis, where sometimes you might need to consider things like heat integration and so forth, but we'll look at that as we go. Now we'll put in a heater. So this heater will take us to our final destination, which is the 450 Kelvin. Then you edit the unit, then you specify the outlet temperature, and we'll go to 450 Kelvin. Now, why am I heating up the stream to 450 Kelvin? So, for example, when you're doing, especially reactor design, when you want to look at the thermodynamics of a reactor, right? What you want is your inlet temperature of your reactants to be similar to the reaction temperature. Because what happens is when you're doing your calculations of your heat of reaction, what you want to have as little effect of the sensible heat to heat up the reactants to come up in your calculation as possible. Then we're going to add your reactor. Again, on the design basis, I mentioned as one of the assumptions that we're going to use the Gibbs model. Now, what I like about the Gibbs model is you do not need to assign a reaction package. Things like a fixed conversion and other models in your COCO will require you to define your reaction, whereas your Gibbs model, it uses what is called the Gibbs minimization, minimization of Gibbs free energy as a model to do the calculation. Whereas you know that for a reaction to be favored, it has to have negative change in your Gibbs energy. So in order to determine whether that equation is thermodynamically favorable, it has to have a negative change in Gibbs energy. This is something that you can also look up in your design textbook and in your reactor theory. So we'll then double click that. Then we go to edit again. Now, reaction will be defined by specifying the compounds, but also the phase that we'll be working on is liquid phase. Then we're going to go to your reactive compounds. Your ethane is an inert, but what is reactive is your benzene. What is reactive is benzene, ethyl benzene, ethylene, and diethyl benzene. If we close that, what you'll see is that your simulation is ready to run again. Then we'll run it. There's a warning. It says suspect value. We'll come back and address that later. Then now what you have is you now have your components. So now you'll see that your ethylene is totally consumed. You still have some benzene left, and then your ethyl benzene is produced, which is 0.12, and you'll see you've got some diethyl benzene. And with this, you'll be able to determine the selectivity based on your simulation, which you can compare to literature data as well. Then the next step is we're going to look at your separation processes. And this is where now you need to decide what is the best way to separate my components. From literature, what I found is that what they do is they use distillation, and they do it in 2 stages. The first stage will separate your benzene, which will be sent back for recycle. And then the second stage will separate your unreacted your basically your ethyl benzene and your diethyl benzene, but and whatever benzene is left in that system. So your bulk benzene will be sent back for the cycle, and then the second stage will separate will purify your ethyl benzene further. So just give me a second. Just want to confirm something before we proceed. Just going back to my cheat sheet. So the other thing I like doing with when I present simulations like this, I like encountering problems as if I'm encountering them for the first time, so that I'm able to equip you as a first-time user of Cocoa with as much tools as possible. All right, so we'll do our first separation, which will be to separate out the benzene. So as I said, from literature, I saw they were doing it using a distillation column. So we're going to go ChemSep column. I'm going to select that. So you see that will come up. Then what we'll do is add that to connect that stream. And then what you'll do is when you double click on your unit, as soon as you click edit, a window will pop up, a small window. I will put it up on the screen now. And then what it gives you is that you can choose between simple distillation, extractive distillation, azeotropic distillation. Is it an absorber or a stripper? Is it a reboiler? Is it a single stage column? All these different functions. Is it the flash, vapor, liquid? And then what we're going to go for is a simple distillation. The one important thing that is critical to remember is you need to change this part here. So instead of keep open, now you need to go ChemSep. The other thing is you need to change your pressure. So we're now dealing with 40 bar. So put the column at 40 bar because we didn't do anything to the pressure. So 1, 2, 3, 1, 2, 3, 4. So that will be 4 zeros. 2, 4, 1, 2, 3, 4. Then we click OK. And then what will happen is your ChemSep window will come up. So what will happen now as a prediction, we might find that the column might not run. So this is something that I've seen. So, but let's first get there. Let me not ruin it for you. Let me not ruin the fun. So now your ChemSep window will come up. Let me bring it up. Now, the way you'll know that you've chosen the right the right function is you should have this on your list on the side. So had you gone keep open, this wouldn't come out, and it would be very difficult for you to get your simulation right. So we'll go to thermodynamics. I like to keep this simple, so I'm going to go Raoult's law, vapor pressure. I'm going to use Antoine. and then enthalpy just ideal. And then we're not going to do reaction. And then the next thing you'd need, everything is specified, but what we need to do is specify the columns. But because it's saying, okay, you can run it as it is, but in this case, I'd like to specify it myself. So we're going to go component recovery and just need to, so your benzene is going to come out on top. So what we'll have is benzene as your top product, and we're going to have that as a more fraction of, oh, I've already specified on top here, sorry. So component recovery, let's go, yeah, component recovery, and let's put it at 0.95. So we're going to recover as much as that. And then bottom specification, we want as much of your diethylene, which is your product, to go there as possible. So let's go 0.98, right? You must always remember to press enter. And then what we'll then do is you close that, and it will ask you, do you want to save the current input? You say yes. Then when you close that, it will ask you to update. Where's that window? I'll just need, yes, to update to update your column. And then you can put in your inlet and outlet streams. Your outlet streams now, because you already have your, so you've got your top product, and then you have your bottom product. The next step will be try to run a distillation column. And then what you'll see is, in most cases, this is a very common failure that I've been getting so far. So I've come up with a trick to solve this. And it's very neat. What you then need to do when you get to a situation like this, detach the incoming stream. So in the column, we're not going to change anything. But what we'll do now is trick the column into solving the problem. So what I've seen is that cocoa struggles with multi-component distillation. So I found that in cases I need to help it create a pathway in order to solve this. So this helps when you use a compound splitter. So a compound splitter will basically, it's not a process unit, but what it is it simply separates out your streams. So when you go to the compound splitter, go edit. So what I want is, I want to do a separation. So in the stream that's going to go to the distillation column, I'm going to have my ethyl benzene and my benzene. Okay. So we're going to close that. So let's run the unit just to check. So you do have the option to calculate a unit on its own. So this stream is the one with the benzene and ethyl benzene. So now you want to take that and send it to the column. So let's run that. I hope this works. It works 9 times out of 10. Because what happens is, as I said, cocoa struggles with multi-component distillation. But once you've now put in just the two products, then you'll see that it now knows that your top product will mainly be benzene. So that was about 99%. And your bottom product will still have benzene, but it will mainly be your ethyl benzene. So what we can then do now is remove our cheat, because right now cocoa has your particular simulation has built in that pathway that will allow, so your column now knows how to separate. So hopefully now that you've removed, it's going to be able to assign everything to where it's supposed to be. Cool. So now what you'll have on your tops, you'll have your ethane that will be going back. So that stream obviously will be building up. As we said, from literature, what usually happens is that your first column separates out most of the benzene, which is recycled back as a feed. And then now what you would need to do is further purify this product stream, which has 73% ethyl benzene, which is your desired product, and more benzene left over. So you basically do it. I do not think we still have a lot of time here, but hopefully we'll be able to finish. I'm hoping because we already showed this particular simulation how to deal with our three component mix, it will be able to automatically do that for this column. Again, as a student, please do explore other ways to set up your distillation column. Look at using reflux ratio. On my side, I'm just using component recovery because that's a shortcut method. But look at your distillation column on your simulation. Okay, again, go to your thermodynamics, keep it simple. Control, ideal. And we go to column specification. Again, we're going to go component recovery. The top one, I'm going to have benzene. I want you to take as much as possible this time. And then in my bottoms, I want as much ethyl benzene as possible. And again, I'm going to go 0.99. Because the minimum is 96%. I'm going to go 99 for now. And then we will bring it back down so that, again, if the column is now too big or too expensive, what you usually do when you're now doing your design of equipment design is you can go back to your process specifications in order to make it cheaper. So in other words, if you are recovering 100%, if you reduce your recovery to 96%, your column may be smaller because of requiring less number of stages. So we need to close that. And yes, we're gonna assign. And then we're gonna update our system. You can see I'm not even looking at the number of stages. That part we will look at the later stage when we go into equipment design. For now, I just want us to look at the process flow sheet, at the PFD, process flow diagram, because your process flow diagram is basically a schematic process description. And that's what we're doing. The first part of your conceptual design is basically coming up with your process description, which will have your PFD, your stream tables, and your written process description. So let's try and run that and see if this unit doc will run. Again, if it doesn't, we'll just then jump to our cheat method to get it to run. The first column seems to be successful. The other thing you can do, so you'll see this when we introduce the recycle stream. Cocoa will get to a point where it will struggle with your, what do they call this? With your iterations. So it will tell you that it's reached its maximum number of iterations. And the way you deal with that is you go to your flow sheet, you go configure, and then you go flow sheet options, and you will increase the maximum number of iterations allowed here. So right now it's only going up to 100, so you can increase that to 500 or 1,000 or whatever the case is. So my top benzene. So now we've got 99%, so very little ethyl benzene. So we check here. We now have 99% ethyl benzene. Again, as I said, if the column becomes too expensive, then we can cut back on the purity that we need on this final distillation column. I'm going to ignore the warnings for now. And then what we want to do is we want to recycle back our benzene. So the first thing I'm going to do is combine the two outlets. Please note you are allowed to rotate this. So if this does cut, I will continue from here. I'm hoping we'll be able to finish this episode. So let's rotate the unit. Looks like I'm not rotating the unit, I'm rotating the labels. Rotate the unit. So we're going to combine those. That one. That two. All right. And then what we'll do is, what I've seen is if your return stream on the recycle is too big, what will happen is your iteration, you reach your maximum number of iterations faster, but also because you've got an inert in your process, it is best to have, I'm looking for a splitter of your recycle to limit the size of the recycle that you're sending back. Because the bigger your recycle, the more expensive your process is going to be, because you're going to require bigger lines, you're going to require larger equipment. So do not throw out your background knowledge in chemical engineering when you're doing this kind of design work. It plays a critical role. So you do need to remember that. You do need to put in those. And some of these considerations are quite common, based on common sense. Like the bigger your stream, obviously, the bigger your pipes, the bigger your equipment, therefore the more costly. And as the design engineer, your job is to design something that will be cost effective. So I'm going to take that. Before I do anything to it, I will then define my split here. So for now, let's go outlet one. So the one going to the atmosphere, or going to the, sorry, not to the atmosphere, going to the flare, or for cleanup, let's make it 70% to start with. Then again, as you know, I like to run my unit operations as I go. All right. Then what we'll then do is we will combine the inlet of benzene with the stream that's coming in now. So instead of this one mixing here, we'll first combine it with the recycle stream, inlet one, and then we've got inlet two. I'm just gonna pull it back, and then this will all join the process. Then just for the sake of saving time, let me just increase the number of allowable iterations so that we don't find ourselves in a situation where we have to come back and do this, because this simulation might take time because of the recycle stream. Now we run it. Again, doing it calculate, so that when the more units you add, right, the more complexity you add to your process simulation, it's already calculated that unit. So which means that it's easier for you to converge to a solution. Very complex simulations can take hours for the convergence to occur. So we'll then find that we still have the product that we require. Then the next part of this will be to produce your stream table, so that we can try and see if we can close our mass balance. So in this case, I will define closing our mass balance as checking if we get the desired product that we need. So this would be ethyl benzene. So I need to rename my stream EP. So now we're going to insert a stream report. And for the sake of closing my mass balance, I just need benzene, ethyl benzene, and EB. And I just need pressure, temperature, flow, and composition. And we're going to copy that. We're going to go back to our mass balance. So let's paste that up here. And just need to change. I just need to change my dots to commas, because my Excel does not like dots. So now what I need to do is we need to confirm if we reach the design requirements, right? So it will be the flow rate of the EB stream, right? Multiplied by the fraction. So that will give us 116 tons, 116 tons per year, which is quite close. But then what you'll then do is you'll then go back and slightly increase your inputs to maybe 15% over design, making that 100 and let me see, if we were 15% over design, then what this will change to is not comma, no, we're going to multiply by over design. Since we've done the simulation, this will be quite quick. So your benzene now becomes, you now go back to your simulation. This will be your benzene stream. Total benzene stream now becomes that. And then your ethylene, let's go back and copy quickly. I'm rushing because I'm hoping Zoom won't kick us out. So Control C, no, we're looking for this stream. Again, because our calculations are related, what happens is when you make a change, you don't have to make it everywhere. So once you change a value, it changes everything on the simulation. And we'll run that again. Hopefully it will run faster because we've already done this. So a mass balance that would otherwise take days to put together, we're able to do within a space of an hour. So that's the beauty of having simulators. And you'll see later when we want to go into equipment design, energy balance considerations. I think we're not going to go into that discussion now because we're rushing it. But now for your energy balance considerations, you're going to look at all your process equipment, because the next step would be to draw a official process flow diagram, approximating how your process is going to look based on this. Sometimes it will look exactly like what you have here, a couple of mixers there and there, a pump and whatever. However, the process flow diagram should approximate what your process would look like in reality. So if it's going to have 3 pumps, you're going to put in 3 pumps. Not backup pumps, but if it's going to have 3 pumps, that will change the conditions of your process streams, right? If, for example, in your reactor, you're going to have a pump around stream, right? If that affects your mass balance, it should be here. If from your reactor to your columns, you're going to have a pump or an expander to decrease the pressure of a valve, that will change the flow conditions. You need to include that as well. I'm going to copy that. I'm going to include that I'm going to paste that again there. Again, just need to do that. And if we check, we're now producing 134 tons per year, right? So I will close it for today. The next session will look at your heat integration. It will look at energy balance considerations. But I guess so far we've done our whole process flow sheet. And then from there, we will look at equipment design. We will look at reactor design. We will look at heat exchanger design. We will look at column design. Thank you very much. I hope this was insightful. I hope you're a bit more passionate about the chemical engineering industries, as I always am. And as I said, my hope is to plant the seeds within, especially the young people. So if you're a parent and you come across this video and your child has been interested in going into the chemical industry, please do show them this video. For kids in high school, I am open to free consultations just to take them through an idea of what the industry looks like. Thank you very much. Have a lovely day, and I hope to interact with many of you as possible.